I think the last slide that we want to spend, the last slide is about randomness and security. Just a moment, I get my, okay. So some words about randomness and security. The point is, for a lot of purposes in security, one of the first things that we would want to have before we are able to solve or achieve any security is randomness. And most of the time when we talk, okay, I feel like I got cut off. How much of it did you hear?
I just heard the title.
Oh, okay. Oh, you lost me for some time then. So in terms of randomness in security, it is a very important issue in security to have randomness. Most of the algorithms that we would start to discuss would start with a notation of randomness. With the randomness, what we mean is that we want to have some random bits that are unpredictable. The meaning of unpredictable, to be specific, we are looking into generating some random bits that, given the nth location bit, then there should be, it should be hard for the adversary to compute the nth plus 1 bit. So this is what we call the random bits should be unpredictable. So soon we would start to discuss about different crypto systems, and over there we would notice that if we don't have, if our bits are predictable, then the entire security of the crypto system could be jeopardized. So this is very important to make sure that bits are unpredictable. And like you've seen that most of the time we talk that we want to choose a secret key, and the secret key should be random. One of the cases that we have encountered that was for one-time pad, and we've seen that in the case of one-time pad, we really want our bits to be random and unpredictable. In addition, that we always have to use the key only once. So it really we have to draw some attention that when we are, in a lot of cases, we just talk about like, we randomly choose a value, or we would randomly generate some bits. And I just wanted to put more emphasis that, the randomness itself has some definition that we would get back to it at some point in the lecture, and we would have a bit more precise definition about random and randomness. And once we've defined those definitions, then we would have a better and thorough discussion about how can we generate random bits, and how, one of the basic questions that we want to basically discuss is that the numbers that we are generating, how random they are, how good they are. Or we would be able to answer all those kind of different questions once we get to the right point. So I just wanted to draw your attention that we really need to pay attention the places that we say, we choose something random. So be very careful that, we would get back to it, and we would pay attention and spend some more time there to see how we can actually choose those random numbers. All right, I think this is the end of the first chapter. So let me just import the next chapter. All right, seems we got to wait a bit. All right. So let's begin our next chapter, which is about symmetric key encryption. You normally start with symmetric one to just warm up a bit, and then eventually we would get down to public key cryptography. The reason that I bring symmetric before public key is because, public key, we have to go through some number theory and some more heavier math than symmetric key cryptography. So this is a good one to just at least easier in a lot of cases than public key cryptography. So that's why we would begin by the symmetric key. So before we get anything through, let's have some define some of the notations that we are going to use throughout this chapter. So we have discussed that we have the key space, message space, and a ciphertext space. So we said that we have a message space. We show them as a set. We have a ciphertext space that would cover all those elements that are in a ciphertext and a message space. So we normally show the message space or the cipher space are equal, and we show them with like 0 and 1s of n bits, right? So we can represent in a binary format every element within this sets, and that we need n bits to represent them. So if you want to think about them in integer format, so we can represent from 0 to all the way to the 2 power n minus 1, right? This would be the range of all integers that we can show in this set. But I think for here, you're not really interested on integers. M could be a message, could be a string, could be a sentence, it could be a message, or it could be a binary file or anything that we can represent it in a binary format. So sometimes we say that we choose a message from a message space. So as we said, these guys are a set. So we said that a message small m from a capital M that represent the entire set of messages, and a small c in a capital S, a capital C that shows a ciphertext from from a ciphertext space. So since we talk about this notation of binary, so let me give you an example. Sometimes you can say that m is equal to 2 as integer, but for binary representation, we have bunch of zeros all the way to 0, right? So this would be n bits. So this would represent the binary format for representing m, which is equal to 2 in integer, or we would consider its binary format. So we would have given this definition. Now we can define our encryption function that would take a key from a key space, would take a message from message space, and it would output a ciphertext. And the decryption function, which again would take the key, the same key, and a ciphertext, and then we would be able to output the message. So we say that for correctness, for any key that we choose from key space, and for any message that we choose from message space, if we encrypt this message first with the same key and then we decrypt it, we should get the same m. So this is just for the sake of the correctness of our algorithm. And we say that from what we've observed over here, the encryption is the inverse of decryption, or vice versa. So decryption is the inverse of encryption. So since that is given, so these two functions are inverse of each other. So let's see how we can observe them in a picture. We have a better observation. So suppose that I have different messages. So I can show M0, M1, M2, all the way to m to the 2n minus 1, right? These are many different messages that I could have. And similarly, I have C0, C1, C2, all the way to C2n minus 1, right? So these are all many ciphertexts that I can have from this set. So when we are talking about encryption to decryption, we are actually talking about a mapping. So M1, maybe we would have many different keys. And, this is the message space. This is the ciphertext space. So the encryption with the key K, that the key is chosen, would take a message and map it to the ciphertext space. And the decryption function with the same key would take the same element and map it back to, the message space. So one way or another, we are talking about a mapping. So for example, when I have set my key, depending on the value of my key, I would map M0 to C1, I would map M2 to M2, and maybe this one to here, and so on and so forth, right? So there would be, different construction or different mappings depending on the different key that I choose. So that being said, so I want you guys to see, the symmetric key encryption decryption system as nothing but just mapping. So it is a one-to-one and onto, so it is a bijective, because otherwise we would miss, when we go from here to here, it should be only one mapping that map M0 to C1, and so that we can do it reverse way, right? So this is some sort of how our symmetric key encryption would look like in abstract. Another definition that we have is that, of course, we want encryption and decryption to be polynomial time computable. So this is also important, because otherwise, if we have an algorithm that satisfies all of this and the correctness, but computing encryption or computing decryption will take a long time, so that would impose a heavy computation on at least one of the parties. And we don't see that algorithm could be a good algorithm because it is not fast enough. And speaking of the security of this crypto system, that we call it informally now, we can define that, okay, we would be able to prove the security of this system under, for example, chosen ciphertext attack only. That over here, it means that, if you remember, we provide the description of the encryption and decryption algorithm to be publicly available. And then we would choose a message, and then we would choose a key at random, and we would encrypt the message. And then we also provide this ciphertext to the attacker. And we are saying that if, nobody can break this system, by mean that nobody would be able to compute M, then that implies that the system or this crypto system is secure under ciphertext only attack. And as we spoke before, ciphertext only attack is not really something interesting, so we are willing to have it to be proven under more stronger a stronger attacker, that is maybe chosen ciphertext attack or chosen plaintext attack. And if some crypto system would be able to resist those kind of attacks, then we would be having more confidence to use them in practice. So the next thing that we want to discuss is the types of symmetric key cryptography. So basically, we have two types. The first one, that we call them a stream cipher, either start to encrypt things on a bit by bit or character by character. So if I want to design this encryption system, I have this box that does encryption, and then here my message comes in, which I can show that bit by bit or character by character, M1, M2, M3, all the way. And then there is another input that my key would go in. So key equals to key 1, key 2, key 3, all the way. And then this algorithm would do the magic, and the ciphertext would come out, which is C1, C2, C3, all the way down, right? So that if I want to define this key function, so for example, we've seen the one-time pad algorithm that encryption of ki and then m of I would be basically, it would output the c of I, right? So it would take a bit of message, the ith bit of the message, the ith bit of the key, and would be able to output the ith bit of the ciphertext. So this is one way to do encryption. And you can imagine that there could be M could be binary, or it could be some characters or some amount of bits that we would be able to process them. But one of the things that we need to be careful is that every time that we want to encrypt a bit or a character, we have to use a different key. So that is one thing to consider. Then at the same time, we have some other types of encryption system that we call them a block cipher. Block ciphers are a little bit different. So it would look like the same. You would take the E, and then a message would come in, and then it would take a key, and then he would output a ciphertext C. And normally it would be able to take a larger M. So for example, the size of M is in RSA, and AES is 128 bits, right? So we are talking about a little bit different algorithms that instead of working on bit by bit or character by character, now it works with a chunk of data, and that chunk of data is some good amount of bits, for example 128 in the case of the AES. And then since we have a different design, then the good thing about this block ciphers is that you can use the very same key to encrypt different messages. You don't have to refresh your key every time you want to encrypt a new message. So you can set your key and use the same key to encrypt multiple different messages, and that would be a very good advantage comparing to the other one, that is stream ciphers, that every time you want to encrypt a new bit, you need to have a fresh bit of key that you haven't used it before, or at least it's not predictable if you reuse it, so that you can achieve this encryption. So you might wonder, why is it so? Why I have to have a stream cipher? And why do we have a block cipher? So let me give you an example. We always discuss this example in the class, that imagine you have, you want to develop an app, that your app is a messaging app, for example, just like Facebook one. So Alice and Bob want to use your app and they want to communicate. So if you use a stream cipher, the moment that Alice starts to type characters, you can just send them over. But if you use, for example, block cipher, then maybe when Alice types hello or hi is not 128 bits. So then it means that you can't send it over to Bob unless if she type a bit more, so that it become 128 bits. Then you can encrypt it and then send it over to Bob. So I'm not sure if you guys seen some some nowadays not very popular, some other apps such as Viber were around, where as soon as you start to type, the other party will start to see what you're typing. You could correct it, the same party would be able to see. And that was very cool for some time to see, to work with such an app that you don't have to hit send, so that the other party would be able to see it, because they use the stream cipher. Any character that you type, your friend would be able to see your message as it is being typed. So that was the advantage of the stream cipher. But if you have block cipher and sometimes you just type hi and you hit send, well, basically your hi is not 128 bits, right? It's just 16 bits if you just see the ASCII codes. So if that is the case, then how you may wonder that how you can transfer it. So we use the idea of padding, meaning that, well, we know that what you have is only 16 bits, but you need to make it to 128 so that your encryption algorithm can actually start to work. So we use the idea of padding so that we add as many zeros as is possible, so that, for example, we make that M, we turn that M into 120 bits. And then once we make that, then we would be able to do that computation. But before converting M to 128 bits, or encryption algorithm wouldn't be able to work at all. So, so the idea would be like you don't have as much good network efficiency as you achieve with the stream cipher as what you would achieve with a block cipher. The reason for that is that in the case of the block cipher, you have to add that extra padding to the end of your message, and that would make you to transfer some extra bits that you won't have to transfer them probably in a stream cipher. So that is one thing to consider when you are developing your app or going to use either a sort of a symmetric key cryptography in the future. You need to see your use case and how you want to send the data to your user, and whether your message is long enough so that you can easily chop it into some smaller pieces and send it to the other party. So for the case of messaging, for example, a stream cipher looked like to be a very good one. But if you talk about like a streaming video, like some techniques that, for example, let's say Netflix, you want to make something like Netflix. So you don't want to send like frame by frame or some small amount. You want to use something like block cipher because your message is long enough, and then you want to chop your message into smaller bits. So for example, 120 bits, 120 bits, and then encrypt it and forward it over. And that would allow you to achieve a higher throughput, because sending such tiny or bit by bit of a video maybe doesn't make sense, or is not a good idea in the first place. The use case of either of these two stream ciphers is going to be depend on the scenario with which you want to utilize them. By the end of this chapter, we will talk about some specific scenarios that would make it easier for you to understand which one is the best for your scenario, and we would have some discussion about them. So the first thing first that we get to discuss today is the notation of perfect secrecy. So we have some formula thanks to Shannon from information. He's a very famous one in information theory. So we can have a definition that with which if a symmetric key crypto system achieve perfect secrecy, then it is equivalent of unconditionally secure, so that even your adversary has unlimited computational power, they wouldn't be able to break the crypto system. And we would start to practice with this. So this is the best we can achieve. And then we would see later on that why for a lot of symmetric key crypto systems, for example, AES, DES, and all other things, we can achieve perfect secrecy. So that is something that we really want to get, but we can get it. And if you remember from the last chapter, we saw that one-time path can actually achieve perfect secrecy. So it is a very good algorithm, but well, it's not practical because of many reasons that we discuss about it. Anyhow, let's see what does it say. So it says that a symmetric key encryption scheme is perfectly secret if for the probability distribution of the message space, and then for every M that we draw, then we have this formula. We get this formula to be satisfied. But let's see what does that mean. Let's break it down. So suppose that my message space is very small. I mean, very small. Let's say it's just 1 bit. So we have 0 or 1. So let's say I have a head or I have a tail, right? Let's say our message space is just like we flip a coin and we want to encrypt it and send it over. So if we say that, we have a coin that is not a perfect coin and it has a probability distribution. So 80% of the time we get head, and then only 20% of the time we get tail, right? So this means that our message space has a distribution. It is not always, half of the time it would be head, half of the time it would be tail. Or you can imagine that this is a message space that a user would answer to some questions, yes, no questions. And, yes and no, depending on questions, that some user has a pattern of 80% of the time saying yes and 20% of the time saying no. So that fact about the user and the choices of the user. But that yes or no, or that fact wants to get encrypted and send it over the channel to the recipient. So what this formula is saying is, in the first place, we need to understand what is this piece of formula over here. So this piece of formula here is a posterior probability about M after given C or after seeing C. So it is a posterior about M after seeing C or given C. Okay. And then, so what is it saying is that the probability for the attacker to guess that the message was M after we show him the ciphertext is nothing but just the distribution of the message itself. So going back over here, imagine we want to design this scenario and the user would get a message that, that let's say a message is head. And then we use encrypt this message. So C equals to E, we encrypt it with K, and then send this C over to adversary. And then what we are saying is that, well, the distribution of the message itself, how many times head or how many times tail comes, is known to the adversary. So that means that given this extra piece of information, C, the encryption of this message does not provide any extra information to the adversary other than what he knew in the first place. So over here, adversary knows the distribution of the message, right? So by showing him, if we draw a value and we just, compute the ciphertext, give the ciphertext to the adversary, he wouldn't be able to learn anything more than just the distribution of the message itself. So in this scenario, if 80% of the time the message is head and 20% of the time the message is tail, sending the ciphertext providing the ciphertext, which is the encryption of head to the adversary, wouldn't really help him to guess what is the message. But the best shot that the adversary has is to just look at this message space and say that, well, 80% of the time it is head. So if I just tell that the output is head, then I would win. Why would I have to check the C, that this C does not give me any extra information? So this is the purpose that we say that it becomes unconditionally secure, or so we can provide unlimited computational power to the adversary, because even though we give him this ciphertext C, even though he does a lot of computation, at the end he wouldn't learn anything more than the distribution of the message space that he knew it in the first place. We are talking about theory here, so I think next week we would go ahead and give you a lot of examples, and we would be able to see that why adversary would not be able to learn anything other than the message space. So some people might argue that why do we give the message space to the adversary in the first place? Why adversary has to know this message space? Well, the point is, a lot of time you can imagine that the phenomena, or that you want to protect or you want to encrypt, is some natural phenomena that is known to everybody. Like maybe I don't have a very good example over here, but let's just say that everybody knows that I have a bias coin, and every time that I use this coin to draw a value, it would have such a distribution. So 80% of the time is head. And the adversary already knows that. But I am flipping a coin and I just want to protect whatever it is showing right now on my coin, right? So maybe it shows tail for 20 consecutive times. This is a low probability, but it can happen, right? It can occur. But the point is, by using encryption, if it is semantically secure, so the adversary would, the best shot of the guess for the adversary is saying that, oh, okay, all of those flips were head, but actually he's wrong because all of the flips happen to be tail in my case, right? So this is how we would argue that in this scenario, so giving the ciphertext to the adversary does not help him in any way. So therefore, even though the adversary has unlimited computational power, that he can solve, even exponential time algorithms in a very quick, in a very short time, then that does not help him in any case, because he can't learn anything but just the distribution of the message in the first place. Given this posterior notation, we can also have this argue that this equation is actually equal to just saying that even if I given that I'm encrypting this message, the adversary cannot learn anything from that by seeing this message, by predicting what the ciphertext for this message could be. Just think it in the other way around. And the other way around to think about it is that for any two different messages that I choose, it is equally likely for them to be encrypted to become the same ciphertext, right? Because the key is here that we are not talking about it. Imagine the case of one-time pad, and the key could be 0 or 1 depending on the different bits of M and M prime. And that can, maybe here the key is 0 and here is key is 1. And if the message is 0 and 1, so you can see that these two would become equal. So we could get the same ciphertext. And then you could see that they would have the same probability. So I understand that, I'm just throwing the formula on the table now. And so starting from next week, we would go through this formula, and then we would discuss and design some crypto systems, and we would apply different strategies for the adversary. And then you will see that there is no other information than the distribution of the message space that the adversary would learn at the end. Okay, let me see. Do we have any questions? Yeah, I will send you the slides very soon. On the slide, and also I will upload the noted slide for the current chapter on the System EE class platform, so that you can access them. All right, any other questions? All right, if not, the class is dismissed, and we'll see you guys next week.
Thank you.